And you don't mind the recording, right?
No, I would like to have a recording.
Okay, that's good. Okay, so let's start. Today, we have one of our own, Professor Stuart Samuel, who was faculty at City College and had a long record. I'm just going to give you a brief record of what he did. He did his undergraduate studies at Princeton University, graduated with the Bachelor of Arts in Mathematics in 75 and 79 with 2 degrees. And then he did his PhD work at UC Berkeley. And then after that, he was member of Advanced Institute at Princeton, faculty at Columbia University, and also faculty at City College. He has worked on multiple different fronts, particularly in high energy physics, on QCD, supersymmetry, some work on string theory, and neutrino oscillations. From what I learned, he also spent some time to some sort of industry positions, I think in the healthcare analysis business. And today we are lucky to have him back, giving us this colloquium about this recent interests about, I think, measurements in quantum theory. So Samuel, it's all yours. Please
Okay.
start.
Well, thank you very much. So the title of this colloquium is The Resolution of the Measurement Problem in Unitary Quantum Field Theory. I have a reference there. It's listed on the slide. You can see it. It's an article on the archive with the title On Wave Function Collapse, the Einstein-Podolsky-Rosen Paradox and Measurement in Quantum Mechanics and Field Theory. The relevant part of that article is section 7 on quantum field theory. I have an alternative title. It's represented by this picture and its caption. I'll let you just look at that for a second. The caption says, "The Cat in the Box" by Dr. Samuel. Okay. So the measurement problem in quantum mechanics. We know that uncertainty exists at small scales due to quantum mechanics. In a nutshell, the measurement problem is as follows. When an experiment is done on a quantum system, why is it that the uncertainty is not manifested at the macroscopic level in experimental outcomes? That is, why is it that we see only one definite outcome? So, as an example, consider measuring a spin 1/2 object with Stern Galak. Suppose an incoming spin is oriented in the x direction. That is, in terms of the quantization in the z direction, it's a linear combination of upspin and downspin. And the spin is going to be measured in the z direction by Stern Galak. Then as the object passes through the gradient magnetic field, the upspin component moves above the z = 0 plane, and the downspin component moves below it. Just before hitting the screen, there are 2 separate wave function states. However, when the object strikes the screen, we only see one flash, either above or below the plane. One explanation is wave function collapse. When the object hits the screen, the wave function collapses to only the up component and a flash occurs above the z = 0 plane, or it collapses to the down component and a flash occurs below the plane. The motivation for wave function collapse comes from the connection between probability of an outcome and the square of the wave function. If the flash occurs above the plane and we know the spin is up, then you would think it must collapse to the upspin component. In other words, we start out with this linear combination of up and down spin, but if we see a flash above the plane, then we know the spin must be up. So the idea of wave function collapse is that the wave function, the spin part of the wave function collapses to the up component. An alternative statement of the measurement problem in quantum mechanics is as follows. When an experiment is done on a quantum system, does either wave function collapse occur, or if not, then why is it that we see only one definite outcome? Almost 2 years ago, I gave a colloquium here at City College entitled The Einstein-Podolsky-Rosen Paradox for the Entangled Spin 1/2 System. The current presentation is based on some of that work, so I'm going to review it here. There is a source that creates a pair of spin 1/2 objects in which the spins combine to give zero angular momentum. You can see the spin part of the wave function here. It involves the spin up of one of the spin 1/2 objects times the spin down of the other minus the opposite combination of spin down and spin up. This has total angular momentum 0. The two objects fly apart a large distance, and they arrive at locations where there are devices to measure the spin. So one of the objects moves to the right, and there's a device there that can measure its spin, and another object moves to the left, and there's a device there that can move to measure the spins. To help the discussion, we'll assume that the left moving object is an electron, and that the right moving object is a positron. And so we'll associate a minus sign with the electron and a positive sign with the positron. Suppose we measure the spin of the electron on the left over here. Then we shall either measure an upspin or a downspin. Consider case 1, in which we measure its spin as up. Then we know that the spin of the positron must be down. Before we could perform the measurement on the electron, or case 2 is the opposite. If we measure the spin of the electron to be down, then we know the spin of the positron must be up. And this is actually seen in experiments. Before we perform the measurement on the electron, the spin of the positron could have been down or up. If the measurement on the electron is associated with wave function collapse, then the spin part of the wave function becomes equal to the first term in case 1, in which the electron spin was measured to be up, and equal to the second term for case 2. In either case, the measurement of the electron on the left has drastically affected the spin wave function of the positron on the right, no matter how far the two are apart. This seems to happen instantly, thereby violating our notion of non-locality, causality, and special relativity. So if the measurement causes a collapse of the spin part of the wave function, then spooky action at the distance takes place. If wave function collapse does not take place, there's actually no Einstein-Podolsky-Rosen paradox. So the Einstein-Podolsky-Rosen paradox is intimately connected with wave function collapse. When an experiment is done on a quantum system, does wave function collapse occur? In the previous colloquium that I gave here, I argued that wave function collapse of the spin part of the wave function for the entangled spin 1/2 system cannot happen, because if it could, 1, there is a gedanken experiment in which angular momentum can be violated. 2, there's a problem with causal coordination when both spins are measured. 3, there's a gedanken experiment in which the Heisenberg's uncertainty principle is violated. And 4, wave function collapse violates the unitarity property of quantum mechanics, which of course is well known. Now, the argument that I provided 2 years ago, I'm not going to discuss all 4 of those. I'm going to discuss number 2. In that gedanken experiment, we modified the spin 1/2 entangled system so that the left measuring device, the one over here, is moving at a relativistic speed to the left, and it starts closer to the source. The speed at which it moves apart and the initial locations of the 3 objects, the source and the 2 measuring devices, can be chosen so that in the rest frame of a measuring device, one of the measuring devices, the corresponding measurement happens before the other measurement. I have a space-time diagram of that. In this diagram, the measurement of the electron spin takes place at the space-time point m sub L, here, here, or here. And that of the positron happens at m sub R, or the right position, space-time point. Diagram A here corresponds to the original entangled spin 1/2 case, in which the source and measuring devices had a common rest frame. For the moving case, in the left experimentalist rest frame, that is in diagram B, the measurement of the positron spin, which happens over here at m sub right, happens after the left experimentalist has measured the spin of the electron. A similar statement holds in the right experimentalist rest frame, given here. The measurement of the electron here takes place after that of the positron. With wave function collapse, the measurement of the electron spin by the experimentalist on the left causes collapse either to the first component or a collapse to the second component, each with probability 50%. This collapse cannot be affected by the measurement of the spin of the positron on the right, because that measurement will happen in the future. The same is true for the experimentalist on the right, measuring the spin of the positron. Half the time, the 2 wave function collapses are incompatible. To be compatible, they both have to collapse either the first term or the second term. But when they are far apart, this cannot be guaranteed. This is a picture of Albert Einstein asking himself, what the heck is going on here? So the third argument I had that I gave last time, almost 2 years ago, was a violation of Heisenberg's uncertainty principle for spin 1/2. For a spin 1/2 object, the Heisenberg's uncertainty principle says that one cannot simultaneously measure the y and z components of the spin. Arrange the left experimentalist to measure the spin of the electron in the z direction, and the right experimentalist to measure the spin of the positron in the y direction. Then with spin wave function collapse, one knows the spin in the y direction for the positron for certainty. And one can deduce the spin in the y direction for the electron with certainty because of the anti-correlation of spins, which not only holds when the axis of quantization is in the z direction, but also holds when the axis of quantization is in the y direction. From the direct measurement of the electron, recall that both measurements happen before the other in their respective rest frames, and therefore cannot be affected by the other measurement. So from the direct measurement of the electron, one knows the spin of the electron in the z direction, and one is able to deduce the y component of spin from the positron's measure, from the measurement of the positron. Hence, one is able to measure both the z and y values of the spin of the electron. This is a picture of Werner Heisenberg, and he's not happy about this situation. Okay, I hit the wrong button here. Given all the difficulties with wave function collapse, for the entangled spin 1/2 system, one concludes that collapse cannot happen. And there is no Einstein-Podolsky-Rosen paradox in quantum mechanics if wave function collapse cannot happen. Last time I presented some of the consequences for measurement in quantum mechanics if wave function collapse cannot happen. So let A be the statement: in a single measurement, one can definitely determine the quantum state. And let B be the phrase: wave function collapse must occur. Then if A implies B, you get the statement: in a single measurement, one can definitely determine the quantum state. If in a single measurement, one can definitely determine the quantum state, then wave function collapse must occur. So if we have a linear combination of upspin and downspin, and a single measurement determines the spin to be up, then wave function collapse must occur. Logic tells us if A implies B, then not A implies not B, and you get what is the converse wave function collapse statement. If wave function collapse does not occur, then in a single measurement, one cannot definitely determine the quantum state. There are some other consequences for measurement in quantum mechanics when wave function collapse doesn't occur. We have the quantum measurement rule. So if wave function collapse is needed to, quote unquote, explain an experimental result, then multiple measurements are necessary to determine the quantum state. But if a single measurement does not need wave function collapse to explain it, then a single measuring event suffices. So imagine that the spin is either up or down, but we don't know which it is. And then we make a measurement, and the measurement indicates that it's up. Then since the state was up and we measured it to be up, no wave function collapse occurred. And so a single measuring event determines whether the spin is up. If we happen to measure it down, then the spin had to be down and no wave function collapse needs to be evoked in this case. But if the spin is a linear combination of up and down, then a single event cannot determine the spin. We also have the macroscopic uncertainty consequence. If wave function collapse does not happen, then quantum mechanical uncertainty at the microscopic level must also appear at the macroscopic level. This statement is embodied in this image, along with the caption. Even Werner Heisenberg is in deep thought. Wow, uncertainty everywhere. One can ask, okay, so this summarizes part of the colloquium that I gave 2 years ago. One can ask whether the arguments against wave function collapse for the entangled spin 1/2 system extend to quantum field theory. So the arguments I gave in the previous colloquium pertain to the case when the theory was governed by ordinary quantum mechanics. The main difference between quantum field theory and ordinary quantum mechanics is that the former involves the second quantization processes of particle being created and destroyed. I shall summarize some of the results in the paper that's on the archive that I wrote. In between particle creation and destruction events, quantum field theory behaves similarly to ordinary quantum mechanics, and wave function collapse cannot occur. During events in which a particle or particles are created or destroyed, I cannot demonstrate that wave function collapse does not happen. However, to avoid argument 2 above or previously, that's the one involving causality and wave function collapse compatibility. Wave function collapse cannot happen instantaneously, but must be delayed because quantum field theory is local and causal. This delayed wave function collapse is actually in agreement with all Bell inequality type experiments. In quantum field theory, unitarity and linearity are valid to all orders in perturbation theory. Therefore, if wave function collapse happens in quantum field theory, then a non-perturbative violation of it must occur, because wave function collapse involves a violation of linearity and also unitarity. During the delayed wave function collapse model that is available on the archive there, the theory is unitary but involves generalized Schrodinger cats during the period in which the wave function collapse has not yet occurred. When a wave function is so when a theory is So a generalized Schrodinger cat is defined as follows. When a wave function is a linear superposition of two or more component wave functions in which the components describe macroscopically incompatible situations. That a wave function, a Schrodinger cat is a wave function which is a linear superposition of two or more component wave functions in which the components describe macroscopically incompatible situations. The famous Schrodinger cat wave function consists of a linear combination of a live cat and a dead cat. An example for the Stern-Galach measurement of a spin 1/2 object would be if the wave function consisted of a linear component involving a flash above the z equals 0 plane and a second component involving a flash below the plane, z equals 0 plane. Everyone is familiar with this quote from Einstein. I cannot believe that God plays dice with the universe. However, if wave function collapse happens, then not only does God play dice with the universe, but the device a rig. He has to use loaded dice. This is due to another problem, a theoretical problem that I did not discuss in the previous colloquium, the Born rule. Given, for example, a spin wave function of the form given here, then the probability of upspin is proportional to the absolute value. Well, so this wave function consists of an up component with a coefficient A and a down component with a coefficient B. The probability of upspin is proportional to the absolute value of the A squared component, and that of the downspin is proportional to the absolute value of the B squared component. So when wave function collapse occurs, one needs, if it collapses to the up component, that this happens with a probability that's proportional to the absolute value of the absolute value of the A squared component. And if it collapses to the second component, the down component, then this must happen with a probability that's proportional to the absolute value of B coefficient squared. But this cannot be guaranteed. For example, the up component could collapse with a probability that's proportional to the absolute value of A to some power P, and the down component could collapse with a probability that's proportional to the absolute value of the coefficient B to the power P. And these are equally good for any P. If wave function collapse occurs and is based on a physical effect, then it's almost impossible for P equal to 2. So if God plays dice, then he needs to rig the wave function collapse so that P equals 2. Let's see. If delayed wave function collapse happens in quantum field theory, then the Born rule must be derived from non-perturbative effects, because wave function collapse is a unitary violating process and is absent to all orders in perturbation theory. In short, there are still problems with the delayed wave function collapse model. So from this point on, let us assume that quantum field theory is unitary and linear, so that wave function collapse cannot happen, and explore the consequences. One of the key steps in showing that the measurement problem is absent in unitary quantum field theory is including the equipment and the experimentalists in the wave function. We shall exploit linearity to the extreme. In quantum mechanics, linearity means that if the wave function is written as a linear combination of two wave functions, then one can solve the Schrodinger equation for each case separately. So if we have the Schrodinger equation for a wave function is given here, and if we write the wave function as a linear combination of any two wave functions, psi1 and psi2, and they don't even have to be orthogonal, then we can solve two equations, the Schrodinger equation for the first component, the Schrodinger equation for the second component, and then take the linear combination of these solutions, that is A times the wave function 1 plus B times wave function 2 to get the solution for psi, the full wave function. Unitarity means the following. Given an initial wave function at time t sub 0, the Schrodinger equation solution at a later time is given by the action of a unitary operator, which depends on the final time and the initial time. So this wave function, the wave function solution at time t sub f, is given by a unitary operator acting on the wave function at the initial time t sub 0. And u is a functional of the Hamiltonian h. When psi is written as a linear combination of two wave functions, unitarity implies that norms and inner products are unchanged with time. So the norm of that first component, psi sub 1, at a later time has to be the same as the norm at an earlier time. When the solution, so psi 1 represents the solution at a later time at t sub f, and that norm is preserved. The same is true for the second component. When you look at the solution for the second component, the norm at time t equals 0 and the norm at time t equals f for any final time are the same. And this is also true for the inner product between the two components. The initial inner product between psi 2 and psi 1 at time t equals 0 will be unchanged with time. It'll be equal to psi 2, the inner product of psi 2 with psi 1 at any later time tf. Consider measuring the spin of a spin 1/2 object using Stern-Gerlach. Suppose the incoming spin is a linear combination of upspin and downspin, A times upspin plus B times downspin, with the absolute value of A squared plus the absolute value of B squared equal 1. Let's use a special detection screen that produces blue light if struck above the z-equal plane, and red light if struck below the z-equal 0 plane. So the initial wave function is psi lab times the spin part of the wave function, A times spin up plus B times spin down, where this wave function for the lab is the wave function of the quantum degrees of freedom of the equipment, the experimentalist, and the non-spin degrees of freedom of the spin 1/2 object. We'll use in linearity. We'll solve the case when the initial state is the first term, namely the wave function of the lab when the spin is up, and when it is the second term when the wave function of the lab times spin down. In the upspin case, the wave function will eventually evolve So something we'll call psi sub up arrow blue. So when the initial state, psi times this up spin arrow, that initial state, the object, the wave function of that involves an object that will rise above the z equals 0 plane. It'll strike the screen and produce blue light, some of which arrives at the experimentalist's eyes, eventually creating, he'll have the thought, blue light and spin up encoded in the quantum degrees of freedom of the experimentalist. So we denote this final wave function as psi with a subscript involving a blue arrow up. Note that the quantum degrees of freedom of the experimentalist cannot contain the thought that there exists a downspin case, because there is none. The whole, we did this whole experiment only involving upspin. The experimentalist is aware of only one outcome, which is the upspin one. Now treat the downspin case. Initially, the state is the wave function for the lab times the downspin wave function. The object descends below the z equals 0 plane, strikes it, and produces red light. The analysis is similar to the case in the previous, than what I've been previously talking about. Denote the final case, the final wave function for this case as psi sub red arrow down. Note the quantum degrees of freedom of the experimentalist cannot contain the thought that there exists a situation in which the spin is up, because there is none when the initial wave function is just involves spin down. If we ran this experiment in which the spin was pointing down, there's no possibility for it to be up. So the experimentalist knows it's down, he sees the red light, and he sees only one outcome, which is the downspin case. Using linearity, the final wave function for the case involving the superposition is A times the wave function with the blue arrow up plus B times the wave function with the blue arrow down. The two wave functions, the one with the blue arrow up and the blue arrow down, are not only different, but orthogonal due to unitarity. And because of linearity, the quantum constituents in the wave function with the blue arrow up do not allow awareness of the downspin case. A similar statement holds for the quantum constituents in the wave function for psi with the red arrow down. Each component wave function is associated only with one seemingly classical outcome, seeing a flash of light either above or below the z-equal plane, but not both. Although we treated the measurement of the spin 1/2 object as a specific case, the following result is true of experiments in general when the initial state involves uncertainty. That is, it's a linear superposition of different quantum possibilities. We have the measurement unawareness result. The experimentalist with the quantum degrees of freedom in his body associated with one wave function component in the superposition cannot be aware of another component in the superposition of the wave function governing a quantum measurement experiment. With the measurement unawareness result, the final wave function, A times the wave function associated with the blue light case plus B times the wave function associated with the red light case, describes exactly the situation experimentally. With probability, the absolute value of A squared, the experimentalist observes the spin to be up and is only aware of it being up, one classical outcome, and cannot be aware of the downspin case. Or with probability absolute value b squared, the experimentalist observes the spin to be down and is only aware of it being down. This solves the measurement problem because it explains why we see only one definite outcome when wave function collapse does not happen. Recall the measurement, this measurement result that I mentioned before, the macroscopic uncertainty consequence. If wave function collapse does not happen, then quantum mechanical uncertainty at the macroscopic level must also appear at the microscopic level, must also appear at the macroscopic level. The final wave function embodies the statement as a linear combination of two wave functions describing macroscopic objects. The uncertainty at the microscopic scale level is transferred to the macroscopic level. The final wave function involves the distribution of the quantum constituents of humans and the laboratory equipment into two distinctive distributions, one associated with the first component and one associated with the second component. This, of course, is a Schrodinger cat wave function. Now I want to discuss the quote unquote, the identity issue. There is another principle governing experiments, the empirical consciousness statement. An experimentalist has the ability not only to observe a result, but also the ability of being aware of it. The empirical consciousness statement is an empirical statement. It does not obviously follow from any physical principles. Humans simply know they have this ability. Why they have it is currently a mystery, is something I don't understand. The empirical consciousness statement plays a role in the identity issue, who am I? For example, if you perform the measurement of the spin 1/2 object in the preceding slides, you will know whether you see blue light or red light. If you know the initial wave function is a linear combination of up and down spin, and unitary quantum field theory is correct, and you believe in it, then you know the final wave function is a form of A times the wave function with blue light and spin up, plus B times the wave function with red light and spin down, the spin down case. Suppose you see blue light, then you know that that is the quantum constituents in your body, are part of the first term, this psi with a blue spin up one. In addition, linearity says that the future development of this wave function, as determined by solving the Schrodinger equation, does not depend on the second component. That's what linearity and unitary tells us. So for practical purposes or for calculational purposes, you can use wave function collapse to the first term. However, you cannot deny the existence in the total wave function of the second term, the one involving psi with the red arrow down, even though you cannot be directly aware of it. The exact same statement applies to the second term, this one, in the superposition, the one involving downspin in red light. If you see red light, you know the spin is down, you know you're part of this component of the wave function. You cannot be directly aware of the first component, and your future is determined by this wave function, this component only, and cannot not have anything to do with the first component. So there's a general, let's see. I'm sorry. Oh, okay, I'm sorry. The quantum constituents of the experimentalist and the laboratory equipment are part of a generalized Schrodinger cat. There's a general rule here governing these situations. When an object comes in contact and interacts with a state that is a linear superposition, such as the one that we've been discussing, involving a linear combination of up and down spin, then the object becomes part of the linear superposition. And then if the object is a macroscopic object, then a generalized Schrodinger cat is produced. So two objects, we need to understand what interaction, when two objects interact. So two objects, A and B, are non-interacting if the total wave function can be factorized. That is, it can be written as a wave function for A times a wave function for B, the wave function for A involving all the quantum constituents of A. It could be many, many degrees of freedom, and the same thing for B. Two objects are interacting if there is no way to express the total wave function in factorized form. Before the experiment takes place, the experimentalist and his equipment have not yet interacted with the quantum state involving the spin. And so the wave function factorizes. It's this wave function times this wave function. After the measurement, an interaction takes place and the wave function becomes this. It no longer factorizes, leading to a generalized Schrodinger cat. So we've been discussing here the total wave function, which is a linear combination of the upspin case and the downspin case. When you see the blue light, you know you are part of the first component of the superposition. For you, what does the second component represent? It involves the quantum constituents in your body, but it is not you because you correspond to the first component, this one. And the wave function of the second component, this one, is different from the first. This second component will have a lot in common with the first component because previously the quantum constituents were part of the same wave function in that psi sub lab. And hence the laboratory wave function, the initial laboratory wave function, and hence have a common past. You'll have, for example, common education, memories, etc., all of which is coded in the quantum constituents of both these wave functions. You might call psi with the red arrow down your Schrodinger twin. However, going forward, the evolution of the second term will be different from the first component. And at some point, these two component wave functions could correspond to something very different, quote unquote, very different. I captured the spirit of what I just said in this cartoon. During this experiment, Eugene Wigner has been waiting outside for the results. And Niels Bohr in the box is performing the experiment. And the caption says here, "I heard I have a twin brother, but I can't seem to see him." By the way, Niels Bohr in the box there is Wigner's friend. So let's go back and look at the entangled spin 1/2 experiment using Stern-Galak measuring devices with the red and blue screens. The total wave function initially involves a laboratory wave function on the left, a laboratory wave function on the right, the wave function for the spin degrees of freedom of the electron and the positron in the angular momentum zero configuration, the wave function for the electron moving to the left, the wave function for the positron moving to the right. After the two spin measurements take place, the experimentalist on the left will observe either blue light, meaning the spin is up, corresponding to the first case here, and that will have to correspond on the right side to red light for the positron, with the positron spin being down. That corresponds to the first term. The second term will evolve to the second term here. So then the two measurements will eventually be compared. So when they're compared, the experimentalists will interact with each other. They will exchange information about whether the electron spin was up or the electron spin was down, and that will influence the thinking of both experimentalists, the one on the left and the one on the right, and therefore they will have their quantum constituents will have to be different from the second spin case. So the wave function psi lab with a blue up spin and a red down spin contains experimentalists who see blue light on the left, the electron spin up, and red light on the right, positive spin down. They'll have their quantum constituents will embody those thoughts. A similar statement holds for the second component, with blue and red interchanged and up and down interchanged. By the way, after the two measurements take place at this point, but before the measurements are compared, each component is factorized, is in factorized form, meaning that the measurement are independent and not affecting each other if you restrict yourself to this case. In other words, when the experimentalist sees the electron spin being up, and he knows that as far as his future is concerned, he can just consider this component, then the wave function is factorized, which makes complete sense physically, because a measurement on the right should be completely independent of the measurement on the left. This final wave function represents the situation perfectly. A 50% chance that the left experimentalist measures the electron spin to be up, with the right experimentalist measuring the positron spin to be down, while not being aware of the other case, this case over here. Or a 50% chance of the opposite spin case occurring. And again, having the experimentalist only being aware of a single classical looking outcome. Because of the empirical consciousness statement, you will know which of the two components corresponds to quote unquote you when you conduct the experiment. So let's see how the resolution of the Einstein-Podolsky-Rosen the Einstein-Podolsky-Rosen paradox happens in this case. It's easy to see how it's resolved in unitary quantum field theory. Suppose only the spin of the electron is measured. So the initial wave function is this, and then we perform, after the measurement on the spin of the electron takes place, then if the spin of the electron is up, then the wave function, the experimentalist on the left and his lab equipment will combine to give you this wave function. On the other hand, if the electron spin is down and red light is seen, it'll combine to give you the second term. From this wave function, which does not involve wave function collapse, one sees that even after the electron spin measurement is made, the probability that the positron spin is 50% up and that the probability is down is 50% down. So the spin wave function of the positron has not been disturbed by the measurement of the electron. So there is no spooky action at a distance. There is no Einstein-Podolsky-Rosen paradox. The traditional Schrodinger cat can be obtained from the Stern-Galak measurement of the spin 1/2 object that we've been discussing by arranging for poison to be released if the lower part, the red part of the screen is struck, and placing a cat in front of and nearby the screen. The experimental setup is shown in the following cartoon. We have the Schrodinger cat and the Wigner dog is performing the experiment. The analysis is similar to what we just did. The initial wave function is as follows. We have a spin wave function that is 50% up, chance of being 50% up and 50% being down. We have the wave function for the cat, and then we have the wave function for Wigner and his lab. After the spin 1/2 object hits the screen, but before the experimentalist has recorded or seen the results, the wave function becomes a wave function involving blue light in a live cat, plus a wave function involving red light and a dead cat. And after the experimentalist has interacted with the cat, the wave function becomes a linear combination of two terms, these two. The final wave function, the final wave function component involving the blue light and the lab with the live cat case involves an experimentalist who has seen a live cat but cannot be aware of the second situation, the dead cat one. The wave function of the second component, which involves red light and a dead cat, involves an experimentalist who has seen a dead cat and cannot be aware of the first situation. Both components involve the observation of a single output, which appears to be classical. The total wave function, this total wave function correctly describes the situation. A 50% chance of each of those, and experimentalists that only see, you will know which of the two cases you are, you will not be aware of the other, and the situation will appear to be classical to you. There are a lot of misconceptions about Schrodinger cats. I'm going to present two here. For example, Roger Penrose, who won the Nobel Prize for work in general relativity, but has also worked on quantum theory, once said, the state of the observer's perception is considered to be entangled with the state of the cat. The perception state, I perceive a live cat, accompanies the live cat state, and the perception state, I perceive a dead cat, accompanies the dead cat state. And indeed, this agrees more or less of what we've been saying. But then he goes on to say the following: I wish to make it clear that as it stands, This is far from a resolution of the cat paradox, for there is nothing in the formalism of quantum mechanics that demands that a state of consciousness cannot involve the simultaneous perception of a live and a dead cat. The last statement is incorrect. We have shown in this colloquium that linearity in quantum mechanics prohibits consciousness involving the simultaneous perception of a live cat and a dead cat. A second misconception is that the Schrodinger cat describes a situation in which the cat is both alive and dead. A wave function of the form A times psi 1 plus B times psi 2, where psi 1 and psi 2 are orthogonal, describes a situation in which case 1 associated with psi 1 occurs, or case 2 associated with psi 2 occurs. So A times a live cat case plus B times a dead cat case describes a situation for which the cat is either alive or dead, but not both. For the cat to be both alive and dead, blue and red light would have had to be emitted from the screen. But the wave function for this case would have had to be of the form blue light, a blue light wave function times a red light wave function. But when the spin 1/2 object strikes the screen, a linear combination of upspin and downspin creates a linear combination of a blue light wave function and a red light wave function, and not the product. If the spin of an electron were to be both up and down, which is contradictory, one would need a wave function of the following form, of this form. Electron spin up times electron spin down, which is not allowed in quantum mechanics. If the spins were associated with different objects, for example, a spin up electron and a spin down positron, then this represents an and situation. It represents the situation of the electron spin being up and an electron spin, a positron spin being down. From the viewpoint of quantum mechanics, there's nothing wrong with Schrodinger cats and their generalizations. There is also nothing wrong with them conceptually and observationally because of the measurement unawareness result and the empirical consciousness statement. Remember, the measurement unawareness result tells us we can't be aware of the other components. And the empirical consciousness statement says that when we conduct the experiment, we're only aware of one of the components. Quantum mechanics involves distributions and fluctuations in the quantum variables. We are well aware of those that occur at the microscopic level. Generalized Schrodinger cats represents distributions and fluctuations that occur at the macroscopic level. It's time to stop the discrimination against Schrodinger cats. To understand better the role of humans, consider the experiment being entirely conducted by a machine. Humans could set it up, but the machine does all the work. The final wave function is as before. So let's conduct this Stern-Galak experiment for measuring spin 1/2. And let's machines only do it. So the final wave function will be as before. But these two wave functions, the upspin case with blue light and the downspin case with red light, involve the quantum constituents inside the machine. Case 1, the machine only records the results. Now, the wave function with the blue light and the upspin is a wave function in which the machine records an up result. And the second component with red light and the spin being down is a wave function in which the machine records a down result. There's no quantum measurement problem here because the machine does not know the phrase only one definite outcome means. Now consider a second case. Imagine artificial intelligence has advanced to the point in which a machine can be aware of the measurement itself. Now, the wave function with the blue light and the upspin is a wave function in which the machine records an up result and also knows it recorded an up result. A similar statement holds for the downspin case with red light, that wave function with the down red arrow. Each component embodies the notion of only one definite outcome. So the machine recorded the result and it's aware of the result, but it's only aware of one definite outcome. There's still no quantum measurement problem because the machine does not know there are two possible outcomes for the experiment. The world appears classical to such a machine. Let's consider, now we turn to case 3. In addition to the abilities of case 2, the machine is taught logic and a little bit of quantum mechanics, including the Born rule, that is the connection between probability and the probability of being in a state and the square of the wave function, and provided with the form of the initial spin wave function. That is, it's a linear combination of up and down spin. Now, the wave function for the upspin case in the blue light is a wave function in which the machine records an up result, and after some reasoning concludes that wave function collapse must have occurred given the Born rule. A similar statement holds for the wave function involving the down arrow and the red spin with up replaced by down. There's no measurement problem here because the machines believe that wave function collapse has resolved the problem of only one definite outcome. Remember, at the beginning of this talk, there were two solutions to the measurement problem. The machines are selecting the first one, namely wave function collapse. Case 4, in addition to the abilities of case 3, the machine is now taught using artificial intelligence that quantum mechanics must be unitary and that wave function collapse cannot happen. So initially, the machine will be puzzled. It'll be going through its logical processes, it'll be puzzled, and we call this case 4A, because the Born rule seems to indicate that wave function collapse must have happened. So early on in the processes, the wave function for the spin up case and the blue light, this one over here, is a wave function in which the machine records an up result. Thinks either non-unitary effects must allow wave function collapse, somehow allow wave function collapse, or if not, things must just work out, and concludes there is a measurement problem in quantum mechanics. However, after more logical processing takes place, the machine will finally reach the conclusion, which is the one in this talk, which I call case 4B. The final wave function is of this form, and this resolves the measurement problem in quantum mechanics because of the measurement unawareness result. I'm sorry. Before the discovery of quantum mechanics, physics corresponded to case 2. Physicists thought the world was classical. After the discovery of quantum mechanics, their thinking corresponded to case 3 or to case 4A. They knew about the measurement problem and either believed in wave function collapse or thought that quantum mechanics is mysterious, hard to understand, and things must just work out. It's time to abandon wave function collapse. It's time to abandon the flat Earth theory. By the way, I might not have defined unitary quantum field theory precisely for you. It is the usual theory you're familiar with, but without wave function collapse. Unitary quantum field theory is a theory that allows us, for example, to calculate the anomalous magnetic moment of the electron to an amazing accuracy, to agree with experiment to more than 10 significant digits. It's the theory where probabilities are based on the Born rule. The interpretation of the theory is obtained by examining the wave function. If you're not sure what I mean by this statement, I have used it many, many times throughout this colloquium. So these slides actually provide you with many examples. The Einstein-Podolsky-Rosen paradox has been around since 1935, more than 85 years. The measurement problem has been around at least as long. In the last colloquium, almost 2 years ago, I argued that wave function collapse cannot happen, and therefore there is no Einstein-Podolsky-Rosen paradox in quantum mechanics. What was unresolved at that time was the measurement problem. What we learned today in this colloquium is that there is no measurement problem in unitary quantum field theory, or in unitary quantum mechanics, as a matter of fact. It is a product of humans whose thinking capacity is limited to machines corresponding to cases 3 and 4a. Welcome to the world of case 4b thinkers. That's the end of the talk.
Very interesting talk. Yeah, so questions, please go ahead. There are some comments thanking on the chat, but
okay, let's see if I can. Let's see if I can access them.
Ishwaran had a comment. Thank you.
Let's see. Okay, I guess there's just 2 comments saying very interesting concepts. Okay,
yeah,
this is a very good question. Yeah, there's a question that says, is this any different from many worlds theory?
Yeah.
So the many worlds theory assigns different worlds to different components of the wave function. And this has a lot of problems. And in fact, it's not so different from wave function collapse. Let me go back and see if there's a slide which will help me discuss this a bit. Well, first of all, let me say that if you assign different worlds to different components, so you run into a lot of problems. For example, I provided some gedanken experiments in which, for example, in the last colloquium, in which angular momentum could be violated. What happens is, if you look and see what happens in the many worlds approach, you'll find that in each world, conservation of angular momentum is violated, and you need the 2 worlds together in order to avoid it. The same thing happens with the Heisenberg uncertainty principle. If you look at that, it's natural to divide in the many worlds approach to have 4 worlds. One in which involves the 2 different spin measurements in the z direction and the 2 different spin measurements in the y direction. And if you assign 4 worlds for those 4 possibilities, then you find that in each of the 4 worlds, Heisenberg's uncertainty principle is violated. it's only when you keep all four components together that you find that the Heisenberg uncertainty principle is not violated. There's really an enormous number of conceptual problems. In this, if you look at what happens here, so in the many worlds, it's really a different theory, not even an interpretation. You don't even know when it happens. I'll come back to that in a second, but the natural thing is when the cat experiences either the poison or not, that there's a world in which the cat is alive and the world in which the cat is dead. Now, what happens here, we have a Wigner who's an experimentalist who's outside the situation, which is we call Wigner in this case. He, from the form of the wave function that you see in unitary quantum field theory, you see that he has to be common to both worlds. So you have a very strange situation where you have a world in which there's a live cat and a world in which there's a dead cat. And then you have a person that has to be in both worlds. And then if he interacts with one of those, like the live cat, then he has to suddenly disappear and become two people in two different worlds. So conceptually, it doesn't add anything. It's really it just creates a lot of confusion. So let me say something else. Let's see here. What is the well, maybe I'll use this as an example. So the question is, when does if this collapses into two worlds, when does it happen? Does it happen with is it always there because of the entangled spin system? Or when the spin passes through the magnetic fields, one component goes up and one component goes down. So the spins are now interacting with the equipment. And if one component goes up, then you have a little angular momentum in the z direction, then the equipment actually has to shift in the other direction a little bit. Is the world being new world being created then? Or is it when the experimentalist sees the light? You just don't know when there's no natural place for when to decide that the world splits into two worlds.
Actually, I asked the question, so do you mind if I just interrupt and comment a little? Because I mean, I'm not an expert by any means, and I'm also still a student. But from what I've read about many worlds theory, my understanding was that it's interaction with the environment and decoherence, and that the many worlds are not a crisp, like exactly defined part of the ontology. They're an emergent part that is, comes out of a very useful way to describe the wave function. But everything that I've read recently about many worlds theory seems to be similar to what you've said, in that it's what happens when you take everything out of quantum theory except for the wave function evolving unitarily.
Okay, so yeah, so that's a good comment. First of all, the role of decoherence. If you noticed, I never mentioned decoherence here. And the key ideas seem to be linearity and unitarity and not decoherence. But this perhaps needs more investigation. I should say some other things, though. In the many worlds, there is some common elements with what I've presented here and the many worlds approach. First of all, there's absence of wave function collapse. That's the starting point. There's no wave function collapse. Secondly, it's very important to include the experimentalist and the laboratory equipment in the analysis. So those elements are common to both approaches. And this approach is actually closer to the original proposal in Hugh Everett's thesis. But this trying to interpret the theory by assigning worlds to it does more harm than good.
Thanks.
Okay. If there is a comment, I don't know if there are minor comments. Stuart on chat.
Okay. Okay, so there's a statement here. Some minor. I thought that Heisenberg changed his view of his microscopic and the application of the uncertainty principle, of saying that one cannot measure incompatible properties exactly to one cannot predict their exact values. Well, so I'm not sure. I'm not sure the difference here, but what I just, you can look at the paper in the archive for the case where you have the gedanken experiment involving the violation of a Heisenberg uncertainty principle. What happens is basically you end up with a wave function that involves 4 components. The 4 components corresponding to the 4 possibilities. Spin being up in the electron spin being up in the Z direction, and say up in the Y direction, and then down in the Z direction and up in the Y direction, and then the 2 other possibilities. So you have all 4 there, and that represents uncertainty. And you can check actually that the Heisenberg's uncertainty principle is exactly satisfied with an equality in that case. It's not greater than or equal, so it's actually an equality. If you have wave function collapse and you see immediately, you end up with a problem. It's very evident. Now you've measured the spin in 2 perpendicular directions exactly. And you can understand then what happens in the many worlds approach, because you have 4 worlds associated with it. And if you live in one world, then and then in each world, there's a violation of the Heisenberg uncertainty principle. So I'm not sure if that answers the first part of the question. The second one says long-range forces seem to belie the possibility that systems can be independent. Now, actually, the way this experiment is supposed to be carried out here is that I've used an electron and a positron here just for pedagogical purposes to help distinguish the left moving object from the right moving object. And so in the case where you have an electron and a positron, you might worry about the long range electromagnetic force. The way the experiment really should be done is that these objects don't have any long range force between them. So their spins get entangled, but other than that, there's no other interaction or entanglement involved. See, the electron and positron spatial part of their wave functions is represented by a product here, indicating that it's not interacting from that point of view. They're interacting only in the sense that their spins are entangled. So when the positron moves very far, or the object, the right moving object, let's not call it a positron, moves way over here, and the left moving object moves way over here, there is no long range interaction between them. So if you have wave function collapse, this creates a tremendous dilemma, because if the wave function, you measure the electron spin on this side, let me go to the let's see. This case, if you measure the spin of the electron or the spin of the left moving object at the, and it turns out it's up and you see the blue light, and then you assume wave function collapsed and this term doesn't appear, then you've created a long range effect on the spin of the right moving object. You forced it to be downward. It could have been up 50%, up or down 50% of the time. Whereas if the wave function still maintains this form, then you don't have an Einstein-Podolsky-Rosen paradox. So I tried to answer the question from Andre Mirabella.
Thank you, Stuart. Very interesting talk,
Okay, you're welcome.
and I think we had nice discussions. We added a lot to material. So
Yeah, it's a great
thank you,
pleasure.
Stuart, again.
It's a great pleasure to give another colloquium at City College. And thank you very much.
Thank you.
Okay.
Thank you, Stuart.
Okay, you're welcome. We can end it
So
here.
I will let me end the recording.
Okay.